Hello everyone. Let's continue our discussion on factors affecting the glitch height. Okay, so we identified another reason, which is the aggressor drive strength. So we know what is aggressor. We have to understand what is drive strength, and also we have to understand what is the impact of the combined effect on the victim, or on the basically on the glitch height. So let's continue. So we take up the same circuit where we have this particular aggressor, we have this particular victim, and the gate that is connected to this end of the aggressor is referred to as driver, and the gate that is following it's referred to as load. So basically this is the aggressor driver that we are talking about. Now we have to check that what should be the drive strength of this particular gate that will affect the glitch height, and how does it affects actually. Okay, so let's take this particular gate out of it and go to the interiors of this gate. For example, if you open up this particular inverter, it has got a PMOS at the top and NMOS at the bottom. Okay, so this is what we have over here. So let's try to look into from a MOSFET point of view. For example, if you put a logic 0 over here, you will see PMOS getting turned on because of the logic 0 over here, and you see NMOS to be turned off. Okay, so let's try to model this scenario over here, something like this. So we know that an on transistor can be replaced by a resistor, and an off transistor can be replaced by an open switch. So we have studied about this in the last videos. So we have just modeled this scenario that we are seeing now over here. So we have replaced the PMOS, the on transistor, which was the PMOS, by a resistor, and the off transistor, which was the NMOS, by an open switch. Now the drive strength will be dependent on the value of this particular resistance. And now we have to find out how will this resistance decide the drive strength of this particular gate, and what should be the value of the resistance to call it as a low drive strength or a high drive strength gate. So let's try to find out that, but this part should be pretty clear. This modeling part, that we replace the on transistor by a resistor. Okay, this part is very clear now. So if you look into if we just for a timing, we don't look into this one, but look into this one. So for example, there is this small opening. There are two openings. There is this small opening. Okay, and when you have this particular opening, you see the resistance will be very huge, because the basic definition of resistance that we have is R is equal to rho L by A. So the area is small over here, and as a result of that, you see a huge resistance. When you see a huge resistance, it means anything that will flow through it will be resisting, or it will be blocking to that. It's basically, let's say, consider a door. If you have a door which is of this size, and there are like 100 people over here. Okay, there are like 100 people in this area, and they have to go through this door. So within a period of time, let's say within 5 minutes, if we have only 5 minutes with us, and within that 5 minute, out of 100, only 30 or 40 people may be able to pass through this particular door in a time period of 5 minutes. On the contrary, if you have a door which is of this size, then within the same 5 minutes, if you have the same 100 people over here, in the 5 minutes you will be able to see that the maybe 90 to 100 people might pass through this particular door and reach over here. So basically, lower the size of the door, it puts lower resistance on the flow. Basically, when we say people are moving from this area to this area, it's basically a flow. So the amount of flow that this particular area brings, that is very low compared to this one. So as a result of that, if you have a smaller area, you have a huge resistance, and if you have a larger area, and you have a huge resistance. Now if we take this particular scenario back to a transistor, what we see is, basically, at the output, whenever you see a scenario something like this says that it's charging the output capacitance. Now what decides that how fast are we charging the transistor or not? That will be decided on the area of this particular area of the PMOS transistor. So area of the PMOS transistor, you can consider this as one of the area of the PMOS transistor, and you can consider this as one of the areas of the PMOS transistor. Okay, so now when you consider this as the area of PMOS transistor, the amount of the current that it will pass through it, so basically we have to charge the output capacitance over here. Okay, and that output capacitance will get charged after we deposit a fixed amount of charges on it. Now those fixed amount of charges will be supplied by the supply voltage, but those fixed amount of charges, just like people, have to move through this particular gate, this particular door. So now if I want to charge the output capacitance completely, the amount of time that this door has to be open will be very huge because of the size of the door, the area of the door. The area of the door is very small, so I have to keep it open for a longer time to charge my output completely. On the contrary, if you have a door like this, if you had the door over here, let's say if you place this one, replace the existing PMOS transistor by a PMOS transistor whose width is so much or whose area is so big. In that case, this particular door has to be open for a very short period of time to charge the existing capacitor over here. So that's the difference that you see. So since basically the drive strength is decided by the amount of time you're keeping your door open. So shorter the time you are keeping your door open, it will decide that it is a high drive strength transistor or high drive strength gate. Longer the time you require your door to be kept open to charge the capacitance completely, that is your low drive strength resistor, low drive strength gate. Okay, so this was about the drive strength. It's basically the amount. And now one thing to notice over here is, in this case, the output capacitance will be charged completely very fast. So in that case, you will be seeing a sharp transition time. As from 0 to 1 there is a transition, so that transition time will be very sharp in this case, because you have a huge area, and so a lot of current can flow through this area and charge the capacitance very fast. As a result of that, you see a very sharp transition time. On the contrary, over here you see a very slow transition time, because transition time basically says how much time is required to transit from 0 to 1. So that is decided by the time required for this particular transistor to charge the output capacitance, and that will again be decided by the area of the transistor. Okay, so this will have a huge transition time, this will have a sharp transition time. So that's what we have concluded over here. So now what we'll do is we'll see the effect of effect of this on the glitch. So let's say we have this particular inverter which is very strong, or basically this particular inverter has very less on resistance, has a very low on resistance. Basically the door is big. That's what we are trying to mention over here by putting dark bold lines. So the door over here is very big. As a result of that, you see a sharp transition time. That part is concluded. Now since the door is so big, the amount of charge that it will deposit on the victim, on the nearby victim, through this coupling capacitance will again be very huge, because the door is so big that it is able to charge itself and the nearby victim. Basically it's able to, so it's like the light. Let's consider a bright light over here. So the light is so bright, it is able to lighten my own house, as well as it is able to throw some light on the nearby house. Now amount of light it will throw on the nearby house will be determined by how strong the lighting effect is, how strong the light is. Okay, so brighter the light, if you have, this particular is like just like a light, it's so bright that it's throwing some amount of light on the nearby charge. So similarly, this particular gate is so strong, it is able to charge my nearby victim. It is able to charge the nearby victim, and the amount of light or the amount of charge that it puts on the nearby victim, that is pretty huge in this case. In a case where your aggressor is very strong, or aggressor has a very strong drive strength, or aggressor has a very big opening. Okay, on the contrary, now we will do not now what we'll do is we'll try to reduce the drive strength. If you try to reduce the drive strength over here, so this is the example with a bigger door. Now we have an example with a medium door, where there will be a decent amount of time that will be required to charge its own output capacitance, which is this, and also a decent amount of light will be thrown on the nearby victim. Basically, an amount of charge that it deposits on its nearby victim is it is there, but it is not very huge. This is still controllable. In contrast to this one, this is still not controllable, because you never know, this particular height of the victim might either go to 1 volt, or it can come back to 0 volt. So you never know in this case, but this case, it's pretty okay. We can say that it can come back to the output. It can come back to ground, basically. In this case, where your resistance is even lower, you see a very huge transition time. So basically, the amount of light that it throws in its own house, that itself is less, and as a result of that, the amount of light that it throws on the nearby house, that is also less. So this is a safe glitch. This glitch is the one that will go through very well. So these were the three scenarios that we tried to explain about the aggressor drive strength. So what we'll do is, in the next video, we'll be looking into one more factor, which is the victim drive strength. So the way we have looked into the aggressor drive strength, we have to look in the similar way to the victim drive strength and see what happens. So let's try to look into all this in the next video. Thank you.